Let us continue the isomerism part. Next, ligand isomerism. Before that, let us discuss linkage isomerism. This linkage and ligand isomerism, these two isomerisms under structural isomerism we have to discuss. First, let us discuss linkage isomerism. Now, the complex compound which are carrying ambidentate ligands, ambidentate. The complex compounds which are carrying ambidentate ligands exhibit this particular isomerism. You know well, we are already classified or discussed thoroughly types of different ligands under based on charge and density and also based on nature of bonding. Under nature of bonding, the ambidentate ligands, you discussed that some of the ligands are carrying two donor atoms, but while in the formation of the complex, only one donor atom is involved, second one is not involving. Such ligands what we call ambidentate ligands. Such ambidentate ligands are there in the complexes, those complexes exhibiting isomerism, this linkage isomerism. Let me give complex CO NH2 taken 5 times, then it is NO2 plus 2, and second one will take same CO NH3 taken 5 times, NH3 taken 5 times, and let me write ONO plus 2. See, one is nitro and nitrito. This ligand is same, but the linkage is different here. This particular one is nitro, the other one is what, nitrito. The formula NO2, there is also NO2, but here cobalt is linked to nitrogen atom, here cobalt is linked to what, oxygen atom. So the ligand which is involving two different donor atoms and forming the complexes, such complexes are known as what, linkage isomers phenomenon, linkage isomerism. Let me give another example. CO, instead of taking CO, let us consider palladium. NH2 taken twice, take CN taken twice. Next one, the same cyano can also involve in bonding as isocyano. Therefore, what, PD, NH3 taken twice, NC taken twice. See, one is cyano complex, another one is what, isocyano. Here it is linked to the palladium through carbon atom, it is linked through what, nitrogen atom. So the ligand is actually the difference in the complexes only due to linkage of the ligand by involving different donor atoms. Next, same palladium, NH3 taken twice, SCN taken twice. Next one, palladium NH2 twice, NCS twice, NCS twice. One is thiocyanato, other is what, isothiocyanato. Here palladium is linked to sulfur, it is palladium linked to what, nitrogen atom. Next, fourth example, you can take CO NH3 taken 5 times, S O2 SO. Thiosulfur to S we call. This is linking through what, sulfur atom. Next one you can write, which is linked through CO NH3 taken 5 times, O SO2 S. This particular thiosulfur ligand, one side is linked through sulfur atom, that is linked through oxygen atom. This is again you put a plus charge here to balance the charges. This is thiosulfate of S, this is thiosulfate of O. So some of the ligands carrying two donor atoms, where in the formation of complex one of the donor atom is only involved. Such ligands are known as what? Ambident ligand. Wherever this particular ambident ligands are there, that particular complexes exhibiting isomerism known as what? Linkage isomerism. Next, let us see ligand isomerism. Ligand isomerism. Yes. Some of the ligands are positional isomers. And these positional isomers, whenever they are there in the different complexes, those complexes exhibit isomerism known as ligand isomerism. What are these positional isomers? Take 1,2-diaminopropane you take. 1,2-diaminopropane. Yes, you are taken in the classification of ligands. 1,2-diaminopropane, PN. We call it what? Propylene diamine, 1,2-diaminopropane. Second one, trimethylene diamine, 1,3-diaminopropane. Trimethylene diamine, 1,3-diaminopropane, PN. See, both are the same ligands, but clearly look here, both are positional isomers. If these two ligands are there in two different complexes, those complexes exhibit isomerism known as what? Ligand isomerism. See how? Suppose this particular two donor atoms of this linked to metal like this, and here these two donor atoms are linked to this particular metal in this way. See, this is what 5-member ring you are clearly observing, and this is what 6-member ring. Ligand is same, but once linkage to the metal is differing, then the ring size is differing. So, once these two ligands are there in the different complexes, those complexes are known as what? Ligand isomers, and the phenomenon ligand isomerism. Many times I have seen a question on this, the ligand isomerism possible by which of the following ligands? Wherever P and T N are there, those complexes exhibit this ligand isomerism. Let us see which complexes are exhibiting this particular isomerism. Say CO, PN taken twice, Cl2. CO, PN taken twice, Cl2 plus to take. Next, let me write CO, TN. TN taken twice and Cl2. TN taken twice, Cl2 and again plus 1. Let me show the structures of these two complexes. You can easily understand how the structures, how they are actually ligand isomers to each other. Now, I am writing the first complex structure, CO, Cl and Cl, 2 PNs here I am linking to the metal CH2, CH, CH3, NH2, this again here CH3, like this. Now, to show the charge, put a bracket like this and represent the charge like this. This is what PN complex. 5-member ring around the cobalt metal. Next one, this particular TN complex I am showing, see the bottom. Cl, Cl, and again we have to link this particular TN, 1,3-diaminopropane, C. This is 6-member ring. One more 6-member ring we write. NH2. These are the complexes. We are clearly observing how they are differing in their structures. These isomers are known as what? Ligand isomers, and the phenomenon ligand isomerism. Next, so under this structural isomerism, we discuss the different types: ionization isomerism, hydrate isomerism, coordination isomerism, coordination position isomerism, next linkage isomerism, ligand isomerism. These are coming under all structural isomerisms. Next part of this particular isomerism, let us see stereoisomerism. Right? Let us see stereoisomerism and discussion about stereoisomerism. Stereoisomerism the complex compounds are having same chemical formulae which differ in the spatial arrangement of ligands are known as stereoisomers, and the phenomenon stereoisomerism. What I say? The complex compounds are having same chemical formulae, which differ in the spatial arrangement of ligands. Spatial arrangement of ligands. Spatial arrangement of ligand. The complex compounds are having same chemical formulae which differ in the spatial arrangement of ligands are known as stereoisomers, and the phenomenon stereoisomerism. This stereoisomerism we are classifying into again two parts. Classified into two parts. One is geometrical isomerism and second one is optical isomerism. Classified into two types, you say, or parts you take, that particular geometrical isomerism and optical isomerism. This isomerism classified into two types. One geometrical isomerism, next optical isomerism. Now, coming to this geometrical isomerism, same definition you can write. The complex compounds are having same chemical formulae and which differ in the spatial arrangement of ligands. Spatial arrangement of ligands are known as what? Geometrical isomers, and the phenomenon geometrical isomerism. Now you see under geometrical isomerism a complex I write Ma2 B2. Complex formula is same. Complex formula is same. Complex formula is same. We can write two different spatial arrangements. See here. So I am writing here two ligands, the same side of the plane. Two ligands in the same side of the plane. We call it as what? Cis isomer. Next one, two ligands we write on opposite side of the plane. Opposite sides of the plane. Then that particular complex we call it as trans. One is cis, the second one is what? Trans. See, the complex compounds are having same chemical formulae but which differ in the spatial arrangement of ligands are known as what? Geometrical isomers, the phenomenon geometrical isomerism. Coming to geometrical isomerism again, take under coordination number 4. Coordination number 4 you take. Coordination number equal to 4. Under coordination number 4, two geometries are possible. One is tetrahedral, takes second one square planar. Tetrahedral and square planar. See under this particular coordination number 4 tetrahedral geometries cannot exhibit this geometrical isomerism. Why? In tetrahedral geometry, each ligand is found to be equidistant from the remaining three ligands. How to show this? Look on the board. How this particular each ligand is equidistant from the remaining three ligands. See now, M. Let me write A and A, B and B. This is tetrahedral geometry. This particular A ligand you consider, this particular A ligand is equidistant from the remaining three ligands. Equidistant from the remaining three ligands. How? This A to A distance, this A to B or this B to B or this particular A to B, all the distances are more or less same. But on the body two-dimensional plane, you cannot easily understand. Look here. This is what imagine as tetrahedral geometry. This is what A ligand. This is also A. This is B and B. Now this particular A ligand is equidistant from the remaining three I said. This A is equal distance to this particular A and this particular B and this particular B. Either you take in between these two ligands and these two ligands or these two ligands, any two ligands, the distance is coming to be more or less same. Therefore, any spatial arrangement, suppose you keep this particular A ligand here, B ligand there, it makes no much difference in the geometry. You are not getting any second geometry. Therefore, tetrahedral geometries cannot exhibit geometrical isomerism. Only square planar geometries exhibit geometrical isomerism. Square plane, this is your square planar geometry. In this particular distance and this particular distance, both the distances are not identical. Therefore, you see here, this says, this we are saying what trans, because this distance is not same to this particular distance. Both the distances are same. Any arrangement you are differing, the ligands are putting under different positions, then you are getting two different structures like this. Therefore, square planar can exhibit this geometrical isomerism, but not tetrahedral. Next, under coordination number 4, we will discuss different types. Before going to discuss about different types, let us have a discussion about this geometrical isomers. Geometrical isomers differ in their physical and chemical properties, remember. Differ in their physical and chemical properties. Suppose you take cis isomer is X in color, this will be Y in color. Their boiling points, melting points, color properties and their reactivity is also not same. They are differing. Why? Once you are taking two ligands on the same side of the plane, next you are taking the ligands on the opposite sides of the plane. Therefore, the reactivity of both never be identical. They differ in their physical and also in their chemical properties. Coming to next, how to identify this particular geometrical isomers. Generally, geometrical isomers are identified by dipole moment values. Dipole moment values. Now, for a cis isomer, dipole moment is very large. For a cis isomer, large dipole moment is C. For a trans isomer, the dipole moment is 0 you take because the bond moments are opposite direction. Therefore, for a trans isomer, the dipole moment is 0 or very less dipole moment is observed. For a cis, very large dipole moment, and for trans isomer, the dipole moment is 0 or it may be very less. Next, when you talk about X-ray crystallographic studies, yes, X-ray crystallographic studies shows that which is cis isomer, which is trans isomer, we can easily analyze it. Coming to the next one, this infrared spectral analysis. Infrared spectral analysis also gives information that which is a cis isomer and which is trans isomer. Now, for a cis isomer, for example, I give absorption bands. For cis isomer, we are getting like this. For example, I am giving. For a trans isomer, the absorption bands are little bit different. Like this. See, the peaks or you say absorption bands are different. This is the IR spectrum of cis isomer, imagine, IR spectrum of trans isomer. According to this also, we can say which is cis isomer, which is trans isomer. So this is the way we identify, we differentiate cis isomer from trans isomer. Next, coordination number 4, scale planar geometry, different types. We will discuss how they are exhibiting the isomerism. Under geometrical isomerism, types under this. Under geometrical isomerism, coordination number 4, square planar geometry, different types. Take the first one. Now, if all the ligands are same, consider Ma4. Ma4 complex is there, plus or minus N. No isomerism. If all the 4 ligands are same, all the 4 corners are occupied by same ligand, what do the second geometry can generate? No. Therefore, Ma4 cannot exhibit any isomerism. Next, coming to Ma3B, you take Ma3B plus or minus n. This we can also write as MB3A, both are one and same. Ma3B or MB3A. Where three ligands are same, and also you cannot generate any second geometry. Whether you have all the four ligands are same, three ligands are same, we cannot write any second structure. Therefore, this geometrical isomerism with Ma4, Ma3B is not possible. No geometrical isomerism, let us say. No geometrical isomerism. Coming to second type, consider Ma2B2. See, at least two ligands are different from the other two. Ma2B2. Next, you take Ma2BC. Ma2BC. Next, you take MABCD. MABCD plus or minus n can exhibit geometrical isomerism. Can exhibit geometrical isomerism. So, exhibit geometrical isomerism. Exhibit geometrical isomerism. Let us see how these are actually showing the geometrical isomerism. Take the first one, Ma2B2 type. Take the real example, if you know, say nickel dichloride diamine, let us take diamine dichloride. You can easily write cis and trans. It's not difficult here. Take nickel, make a scale plane or geometry, right? Cl and Cl, NH3 and NH3. See, cis complex. Cis. Trans complex. Trans complex. Cl and Cl I am writing on the opposite sides. This is what to say trans, cis and trans. No difficulty, well known to you. This is cis, that is trans. Let me show the next one. Ma2B2, Ma2BC. Ma2BC. Look what difference we are making here. Very simple difference here. Two different ligands are there, right? A2B2, A2BC. BC means to write one is Cl, one is Br. One is Cl, one is Br. Simple way, this particular complex says that it trans. Just we change this. Instead of writing two chloride ligands, one is chloride, one is bromide. Very simple to write this. Now, this is what the Br, this is, take it as the Br, then you can say one is cis, the other is what the trans. This is important again, MABCD type, four ligands are different in the scale plane or geometry. This is coming, this is actually important. Many times question on this MABCD type is appearing in the different entrance exams that you have to concentrate more. Let me show that MABCD type. See the next one, MABCD. MABCD plus or minus n. Take an example, what you remember, say four ligands you have to keep different. Let me write a platinum complex, platinum, NO2, NH3, PY, NH2OH, right? These are this is the complex. Put a plus charge to make the oxidation number +2. This is scale plane complex. We are clearly looking, all the four ligands are different. But I said three isomers are possible. This is very, very important model. Remember, three isomers are possible. Three isomers are possible. Three isomers are possible. Now, How three isomers are possible? First I write A is trans to B, A is trans to C, A is trans to D. Either you take the cis relationship or you take the trans relationship. Only three isomers you can write. Fourth you cannot write. Look, write the fourth and check. Definitely the fourth will be identical to either of the three. Let us see how we could be able to write this particular three isomers. Square planar. When I will fix first one, fix anything, suppose I make it NH3, I am fixing here. Then I am writing first NO2. Remaining I will write like this, NH2OH. Okay, this is what we write is NO2 is trans to NH3, I will write. NO2 is trans to NH3. NO2 is trans to NH3. Next, we change this particular ligands again. Second one I am writing. Observe this. Again NH3. I write PY. Just NO2. Then NH2OH. What do you say this one? PY is trans to NH3. PY is trans to NH3. PY is trans to NH3. Next, third one, look here. NH3, I write NH2OH. Then you keep this particular NO2 as here and let us write P1. What is this particular complex now? NH2OH is trans to NH3. See, first one NO2 trans to NH3, PY is trans to NH3 and NH2OH is trans to NH3. Now you see one more complex and write and see. That particular definitely will be identical to either of the three. Only three isomers are possible. This is a very important model. Many times this is appearing in the different entrance exams. Next, let us see square planar geometry. We have seen only monodentate ligands. Once a bidentate ligand comes, once bidentate ligand is there in the square planar complex, then how that is exhibiting isomerism? Let us see a complex with the bidentate ligands. Square planar with bidentate ligands. Square planar with bidentate ligands. Bidentate ligands. But one more thing is very important here. With symmetric bidentate, no isomerism. So what I am writing, see on the board, with symmetric bidentate, symmetric bidentate ligands, no geometrical isomerism. With symmetric bidentate, no geometrical isomerism. What do you understand by this? See, symmetric means the two same donor atoms, a bidentate ligand carrying two donor atoms same. Look here, MAA taken twice, plus or minus N. Real example I write to see, take nickel ethylene nickel EN taken twice plus 2. No geometrical isomerism. Why it cannot exhibit the isomerism? All the four corners are occupied by nitrogen donors. I will write the structure and see. Here I will put it, or let me show here only, right? Nickel linked to ethylene amines, C. make scale planar geometry. This is CH2, CH2, NH2. Another one, this one. See, all the four corners are occupied by nitrogen atoms, clearly looking. What you can generate the second geometry? No. In anyhow, we cannot write any second geometry for this. Therefore, what we say, this particular complex is not exhibiting geometrical isomerism. Which one will exhibit? A scale planar complex with the unsymmetric bidentate. With unsymmetric bidentate. With unsymmetric bidentate ligands. Bidentate with unsymmetric bidentate ligands exhibit geometrical isomerism. What do write unsymmetric means? Two different donor atoms, right? M, AB taken twice, plus or minus N. This one will be, let me say, nickel glycinato taken twice. Nickel glycinato taken twice, you know, glycinato ligand, two different donor atoms, one is N and one is O. With this particular, I will show the geometrical isomerism. Now, first one let me write. I will remove this and I will show how this particular geometrical isomerism possible by nickel glycinato. See, Ni NH2, CH2, C double bond O. Next, cis complex I am writing now, CH2, C double bond O, NH2. How we write NH2? This is, should be O. CH2, C double bond O. This is cis complex. Let us develop again trans complex. CH2, C double bond O. Here I am writing transposition NH2 group. Right. CH2 double bond O. One is cis, one is trans. So, scale planar complexes with the monodentate ligands, scale planar complexes with bidentate ligands. One thing you have to remember, with symmetric bidentate, no geometrical isomerism, only with the unsymmetric bidentate. Unsymmetric bidentate means the bidentate ligand should carry two different donor atoms. Then only this geometrical isomerism is possible with the scale planar complexes.